so how to solve right triangles, Miss McBride, objective. Learning objectives for lesson 1. Alright, so we will learn the properties of a right triangle, Pythagorean theorem and its application in solving for right triangles, trigonometric ratios and how to use them to solve for right triangles, and lastly, the relationship between the trigonometric ratios and the Pythagorean theorem. Go to right triangle properties. Alright, so as a warm-up, I asked the students to use GeoGebra to demonstrate a right triangle and to label it and to show some of its properties. Alright, so I made a video which I'll add to my quick links that the triangle has a 90-degree angle. The sides are labeled A, B, and C, where A is leg 1, B is leg 2, and C is the hypotenuse as indicated over here. I also indicated that all three angles when added up are equivalent to 180 degrees. And specifically for a right triangle, these two angles right here and here are complementary angles as shown right here, and they sum to 90 degrees. Alright, so properties of right triangles. It is a triangle that has one right angle that measures 90 degrees, denoted by a square inside the triangle, right here. Its sum of its angles is 180 degrees. Its largest side is called the hypotenuse, and it is located across from the right angle. The other two sides, A and B, are called the legs. And the two non-right angles, these two right here, they are complementary, which means they add up to the sum of 90 degrees. And finally, the three sides of the triangle, A, B, and C, satisfy the Pythagorean theorem, which we will discuss later. So special right triangles, we'll start with the 45-45-90 triangle, or the isosceles right triangle. This type of right triangle has two angles that are equivalent. This also means that the two legs of the triangle have equal length. A 45-45-90 triangle represents the two equivalent angles and the one right angle, which is right here. Its side length ratio is x to x radical 2, where the ratio represents leg 1, leg 2, and finally the hypotenuse. Special right triangles continued. We have the 30-60-90 triangle. This is a right triangle that has angles of 30, 60, 90 degrees. Its side length ratio is x to x radical 3 to 2x, where the ratio represents the short leg, which is right here, to the long leg, right here, to the hypotenuse, right here. Examples using special right triangles to solve. So what is the value for x? So here are our steps. First, we use our knowledge of isosceles right triangles, and we know to recognize that this triangle specifically has one 90-degree angle and two equal sides. We solve for x by recalling that there is a side length ratio of x to radical 2 times x. Alright, thus our leg 1 has a length of 6, our leg 2 has a length of 6, and we can deduce that x, the hypotenuse, is going to be 6 radical 2. We can also acknowledge that our two acute angles will both be 45 degrees, right here and right here. So examples continued. What is the value for x? So using our knowledge of 30, 60, 90 triangles, we can identify that this triangle has one 90-degree angle and one 60-degree angle. Thus, we know that the third angle has to be 30 degrees. Step 2. So now that we know for sure we have a 30, 60, 90 triangle, we can use our knowledge of side length ratios where short leg to long leg to hypotenuse is in a ratio of x times radical 3 and 2x. We plug in our known side length values to determine the length of the long leg. So that it would be 2 radical 3. Alright, so that's the long leg length, 2 radical 3. Alright, so what is the Pythagorean theorem? The Pythagorean theorem is written in the form a squared plus b squared equals c squared. It is used only for right triangles. The theorem shows that if squares are made on each of the three sides of a right triangle, then the area of the biggest square is equivalent to the sum of the areas of the two smaller squares. C represents the hypotenuse, or the longest side, whereas A and B represent the two legs. When given the lengths of two sides of a right triangle, but the Pythagorean theorem can be used to find the length of the third side. So I did a proof of the Pythagorean theorem on GeoGebra. Below is just a quick visual of this end product of the theorem. Alright, in this demonstration I'm just showing that as you change the dimensions of this right triangle, like the lengths of the sides or the angles, then you see that the a squared plus b squared equals c squared formula changes with it. And in all cases, it stands correct, where the sum of the areas of the two smaller squares is equivalent to the area of the largest square. Alright, so Pythagorean triples. It is a triple of positive integers that satisfies the Pythagorean theorem written in the form a, b, c. Two examples of Pythagorean triples are 3, 4, 5, and 5, 12, 13. Alright, so this is our first example of how to use the Pythagorean theorem to solve for right triangles. Solve for x given the triangle below. So our first step is to analyze what we have. So we know that a is equal to x, b is equal to 8, and c is equal to 10. Step 2 is x squared plus 8 squared equals 10 squared. So essentially we plugged our numbers into the formula. Step 3 is x squared plus 64 is equal to 100. We did 8 squared, we got 64, and we did 10 squared, we got 100. Step 4 is x squared is equal to 36. In this step, it is clear that we subtracted 64 from 100, and we got 36. Step 5, we get x is equal to 6, and we did this by taking the square root of 36. So note, this triangle follows the ratio of 3n, 4n, 5n for ABC, so it is a Pythagorean triple. What is the value for x? So this is example 2. We do the same process where a is equal to 20, b is equal to 21, c is equal to x. Step 2 is we plug in our values into the formula. We have 20 squared plus 21 squared is equal to x squared. Okay, and we get in step 3 that 20 squared is equivalent to 400, 21 squared is equal to 441. We add those two values together and we get 841 is equal to x squared. We take the square root of both sides and we get x is equal to 29. Alright, so in class we did a simple activity where I had the students demonstrate their knowledge of the theorem in GeoGebra. It wasn't a proof. Students just had to make a right triangle, show that it had a 90-degree angle, show that each of its sides were a, b, and c, and demonstrate the formula of a squared plus b squared equals c squared by plugging into the input bar each of the sides squared and then plugging them into the formula to demonstrate that it works. Alright, so trigonometric ratios, what are they? So they are ratios that are only used for right triangles. They demonstrate the relationship between sides and angles, and a helpful mnemonic device is SOHCAHTOA, which stands for sine, opposite, hypotenuse, cos, adjacent, hypotenuse, tan, opposite, adjacent. So let's define terms. So hypotenuse is the side across from the right angle and it's the longest side. Adjacent is the side adjacent to the non-right angle, essentially the angle that we're looking for. And opposite is the side opposite the non-right angle. Okay, so what exactly are the three main trig ratios? So we have sine theta is equal to opposite over hypotenuse. We have cos theta is equal to adjacent over hypotenuse. And we have tan theta, and that's equal to opposite over adjacent. And we have our diagram right here. This is the angle we want. This is the opposite side from it. This is the adjacent side. And this is the hypotenuse. So let's continue. The reciprocals of the three trig functions are as follows. Cosecant theta is equal to 1 divided by sine theta equal to hypotenuse over the opposite. Secant theta is equal to 1 over cos theta is equal to the hypotenuse over the adjacent. And lastly, the cotangent of theta is equal to 1 over tan of theta is equal to adjacent over opposite. Finally, let's do some examples. So how to solve right triangles using trig ratios. So let's solve for theta. So the first step is to identify which trig ratio to use by recognizing what is given. We are given the opposite side and the adjacent side to the angle right here. So we will use tan. Step 3 is tan of theta is equal to opposite over adjacent. So we write tan of theta is equal to 6 over 8. So theta, therefore, is equal to tan inverse of 6 divided by 8. So using your graphing calculator, press second tan to get tan inverse, and then plug in the value 6 divided by 8. Make sure that the calculator is in degree mode. All right, and then finally, we get theta is equal to 36.87 degrees. All right, let's continue. What is the value for x given that theta is 30 degrees? All right, so step 1 is evaluate what you are given and what you want to solve for to determine what trig ratio to use. We are given one angle of 30 degrees and the hypotenuse length of 16. So we need to use sine. We plug in our values into the trig ratio for sine, and we want to solve for the opposite side from the angle. Make sure the calculator is in degree mode, and directly type in sine of 30, and you will get 0.5, and you set that equal to x all over 16. Multiply 0.5 and 16, and you'll get x is equal to 8. All right, so again in class, we used GeoGebra, and the students, they showed the relationship between two sides and one acute angle of the right triangle. And they only had to use one of the trig ratios. So this is just an example that I made. I showed the relationship between sides AC with angle A using the sine function. So we have sine of 41.92, which was the angle. All right, and I typed that into the input bar. I got 0.67. All right, and then I also did the side length A divided by side length of C, which is 3.63 divided by 5.44, and that's equivalent to 0.67. All right, and we know that, sine of alpha or sine of theta is going to be equal to opposite over hypotenuse. All right, so in this situation, sine of 41.92 is going to be equal to the opposite, which was 3.63 right here, all over the hypotenuse of 5.44 right here, and we get the answer of 0.67. All right, so what is the relationship between trigonometric ratios and the Pythagorean theorem? A squared plus b squared equals c squared is a Pythagorean theorem, and sine of theta is equal to opposite over hypotenuse, or also written as a divided by c, as shown in this diagram right here. All right, so opposite over hypotenuse, a over c. We also have cos of theta is equal to adjacent over hypotenuse, which can be written as b over c. All right here. So if we want c squared to cancel, right here, we divide the whole formula by c squared. All right, so this was our formula. We divide everything by c squared, and we get a divided by c squared plus b divided by c squared is equal to 1. So we know that sine of theta is equal to a divided by c. We plug it in. And we know that cos of theta is equal to b divided by c. We can plug that in. And then we square our values, and we get sine squared of theta plus cos squared of theta is equal to 1. So thus we use trig ratios to transform the Pythagorean theorem into a trig identity. Closure. All right, so our summary of our cases. So we have case 1, given two sides, and we want a third side. Use Pythagorean theorem when you are given two sides of a right triangle and are asked to find the third side. Case 2, given two angles and we want a third side. If you are given a right triangle and given the value of one acute angle, you can use your knowledge of right triangles. Use the fact that the two acute angles in a right triangle sum to 90 degrees to find the third angle. Case 3, given two sides and want one acute angle, or we are given one side and one acute angle and we want to find another side. We can use trigonometric ratios to find the value that we want. In case 4, given a right triangle that matches the qualities of one of the special right triangles, you can solve for angles or the sides. Finally, food for thought. Think about what real-world scenarios might require the Pythagorean theorem or trig ratios. Any questions about the lesson, please email me. And homework is due tomorrow morning and it has been posted to the website.